Hello, everyone. I wanted to make a quick video for you about Rolle's theorem since we did not get to it in class today. Um, the good news is that Rolle's theorem should be pretty simple and it's going to be very consistent with what we did in class today. Okay, so Rolle's theorem says let f be a continuous function on a closed interval. So this is also where we started with the extreme value theorem, where um, our function is going to be continuous and we have a closed interval from x equals a to x equals b. So we've got closed circles at our endpoints and nothing weird happens to our function over that interval. We don't have any no breaks, no jumps, no holes, no vertical asymptotes, nothing weird. In addition to that, now our function is also differentiable on the interior from A to B. We don't have to be differentiable at our endpoints at x equals A and at x equals B, but we do need to be differentiable everywhere in between. Okay, so our function's continuous, we have a closed interval, and we're differentiable everywhere in the middle. So if f of A is equal to f of B, that means if the y value at one endpoint is equal to the y value at my other endpoint. I'm just going to draw a picture here to make sure I understand. Here's x equals A, here's x equals B. I have a continuous function from one side to the other, and we're equal at the endpoints. So let's say both of these y values are equal, and I'm going to call that value, I don't know, L. So if our endpoints are equal, then, and we have a continuous function in between, then there exists, I'm going to write this in math notation and then I'll put in the extra ones. Hopefully you're starting to get comfortable using some of these math notation symbols. So this backwards E is there exists a C value. So x equals C in our interval A to B such that f prime of C is equal to 0. Okay, so let me put in this is there exists. This is in. This backwards one is such that. Okay, so if we have a continuous function on a closed interval that is differentiable on the open interval, then as long as our y values are the same at the ends, we have to have some x value, x equals c, where our derivative, the slope of our tangent line, is equal to 0. So basically, if we're continuous in here, there has to be some place where we change direction, right? If we go up or down from L, we're going to have to change direction and come back so that our y values are equal. There's going to be a c value in here where the derivative, the slope of my tangent line, is 0. I have a horizontal tangent line. And we could have many of these. It says there exists, means there exists at least one. We could have multiple of these. So let's say our function does something like, so let's say we start and end at the y value L. If our function does something like this, then we're going to have one here. And we're going to have one over here as well. Right here, we're going to have two C values. But because we're continuous, if we go up or down, we're going to have to change direction to come back down. And that means that we're going to have a place where we have a horizontal tangent line. We have to have that critical point in there somewhere. And because we're differentiable, that means that f prime of C has to equal 0. There will not be any places where f prime of C does not exist in our interval. So that's why these are the only kinds of critical points that we have. And notice even like the really strange case, kind of the weirdest case that we could have is if your n values are the same, if you don't go up or down, then you're flat. And that means that you have a zero slope every point in here, which means every point between A and B could be a C value. So you have infinitely many. That's kind of the strangest case. But basically, if you aren't completely flat, then if you go up at all, you're going to have to change direction to come back to being at your end point. Or if you start by going down, you're going to have to change direction to come back. Okay, so that's what Rolle's theorem says. If your endpoints are equal, there's a spot with a horizontal tangent line. Okay, now to verify Rolle's theorem for a function on a closed interval, before we apply Rolle's theorem and just find the place where f prime of c is equal to 0, we first have to make sure that we check all of these boxes. Remember, in order to have this, f needed to be a continuous function, and it needed to be differentiable on the open interval, and we needed our y values to be equal. We have to check all three of those boxes before we can apply Rolle's theorem and be 100% sure that we have a c value in there where our tangent line is horizontal. So we first have to check those boxes. So let's start with, if we have a function f of x is equal to x to the fourth minus x squared, and I want that function over the closed interval from -2 to 2. The first hurdle that I have to get over is my function continuous on my closed interval from -2 to 2? Is this function continuous everywhere there? Yes, it's a polynomial. Polynomials are continuous everywhere. So that means it's continuous from -2 to 2. So that's a quick check. Number 2, is f of x differentiable on my open interval from -2 to 2? Well, we got to make sure that our derivative exists. So f prime of x is equal to 4x to the third minus 2x. This exists everywhere. I don't have any place where my derivative fails to exist. This is differentiable everywhere. So it's also differentiable from -2 to 2. So I check that box as well. And then the third one that we have to check is f of a equal to f of b? Are the y values at my end points the same? Well, my endpoints A is -2 and B is +2. So I'm just going to double check this quick. F of -2, to find my y value there, I'm going to come to my original function, and I'm going to have -2 to the fourth power minus -2 squared. And when I plug that in, I'm going to get 16 minus 4, which is 12. I'm going to do the same thing with my b value. I'm going to plug in a +2 here. I'm going to get 2 to the fourth minus 2 squared. And again, I'm going to get 16 minus 4. That's still 12. These are, in fact, equal. So I've checked all three boxes. That means Rolle's theorem applies to this function on this closed interval, which means I'm guaranteed a place where my derivative is 0. So I'll say, thus, there's a place where f prime of c is equal to 0. Let's find it. So I'm looking for the place where my derivative equals 0. To find that c value, I'm going to take my derivative, which we found up here. I'm going to set it equal to 0. I'm going to solve. So 0 is equal to 4x to the third minus 2x. And I'm going to solve this out again with factoring. I'm going to take a 2x. I've got x squared minus 1. Oh, there's a 2 here. Sorry. 2x squared minus 1. That's more accurate. All right, so that means either 2x equals 0, which means x equals 0 is our first c value, or 2x squared minus 1 equals 0, in which case 2x squared is equal to 1. X squared is 1/2, which means x is plus or minus 1 over the square root of 2. So I get 2 c values from that one. So we actually have 3 places from -2 to 2 where our derivative is equal to 0, because 0, 1 over root 2, and -1 over root 2 are all in this interval. So we're going to keep all of them. So our c values are x equals 0, x equals 1 over root 2, x equals -1 over root 2. Those are all of the places guaranteed by Rolle's theorem. We've got 3 c values there. Okay, cool. So let's try the next one. For g of x is equal to x squared over 5x minus 8, I want to find all values in 2 to 8 where f prime of c is equal to 0 by Rolle's theorem. So that means that we're really looking at g of x equals x squared over 5x minus 8 on the closed interval from 2 to 8. So I need to be continuous on the closed interval. So first box that we have to check is g of x continuous on the closed interval from 2 to 8? Okay, well, gotta take a look at this function. And I'm looking for where this function is continuous. Well, because this is a rational function, I need to be careful. There's a place where this is not continuous. G of x is not continuous where my denominator is equal to 0. So this is not continuous where my denominator of 5x minus 8 is equal to 0. And that means that x would be 8/5, and 8/5 is 1.6. So it's not continuous where x is 1.6. But that's outside my interval. My interval goes from x equals 2 to x equals 8, which means I'm continuous everywhere but 1.6, which means I'm good on 2 to 8. So we are A-okay. My discontinuity happens outside my interval. I just need to be continuous in my closed interval. So that's fine. And then number 2, the second hurdle that we have to get over here is my function differentiable on the open interval? So are we differentiable between x equals 2 and x equals 8? Well, to figure that out, we need to see what g prime of x looks like. To figure out the derivative of this guy, I've got something with x's in it divided by something with x's in it. I'm going to use the quotient rule. So I'm going to do low, which is 5x minus 8 times d high, the derivative of the top, which is 2x, minus high, which is x squared, times d low, the derivative of the bottom. The derivative of 5x minus 8 is 5. And then all over the bottom squared, 5x minus 8 squared. Here's our quotient rule. That's what my derivative looks like. Let's simplify this and see what we've got going on. So I'm going to have 10x squared minus 16x minus 5x squared all over that denominator. And then I can combine like terms here. So I'm going to have 5x squared minus 16x all over 5x minus 8 squared. All right, so that's what my derivative looks like. Is this differentiable from x equals 2 to x equals 8? Well, this derivative is going to exist as long as the denominator is not 0. Okay, so we're differentiable everywhere except, that's a T, except where my denominator equals 0 and that's where 5x minus 8 equals 0. We just did this. X is 1.6, right? It's that 8/5 or 1.6. I'm not differentiable there, but that's still not my open interval. So we're still good. We're differentiable from x equals 2 to x equals 8. This is outside my window. So we're good. We are differentiable on the open interval. The last thing that we have to check is g of a equal to g of b? Are my y values at my endpoints the same? Okay, so that means we need to check g of 2, and in which case I'm going to get 2 squared over 5 times 2 minus 8, which is 4 over 10 minus 8, which is 2, and I get a y value for 2 when x is 2. We also have to plug in our other endpoint here, which is x equals 8. When I plug 8 in, I'm going to get 8 squared, 5 times 8 minus 8. I'm going to get 64 over 40 minus 8 is 32. 64 divided by 34 is 2. These are the same, and so that box is also checked. My endpoints are the same. We've checked all 3 boxes to make sure that Rolle's theorem applies, and now we just have to find all of our c values that make our derivative equal to 0. So we are going to say we want to find the places where g prime of x, which we found was 5x squared minus 16x all over 5x minus 8 squared equals 0. We kind of talked about this in class today. This whole fraction is only going to be 0 where the top is equal to 0. So this is going to happen where 5x squared minus 16x is equal to 0. And I'm going to factor to solve this. And x is the best thing I can factor out here. So I've got 5x minus 16 equals 0. So either x equals 0 or 5x minus 16 is 0. If 5x minus 16 is equal to 0, then x is 16/5. And those are the 2 c values that are guaranteed by Rolle's theorem. Our c values are either 0 or 16 over 5. If you put that in a calculator, you will get 3.2. I'm good with either one of those. And that's Rolle's theorem. So really, we're just looking for the places where our derivative is equal to 0. But before you do that, you have to make sure that you check all of these boxes. You have to be continuous on the closed, differentiable on the open, and your endpoints have to be the same. They have to have the same y value. So I hope that helps with Rolle's theorem. Have a lovely weekend, and I will see you next time.